This is a video explaining some of the reflection behavior you saw in the lab that you've done this week. Just a reminder that reflection is the part of the wave that stays within the original material, and it's kind of what bounces back after the wave encounters a boundary. All right, so we're going to start off with a video of wave reflection, a real life example. This is a spring that is attached to a fixed end. And we're going to watch the slow-mo here. So I have the video kind of queued up part way in. You can see that they send down a wave on the right side of the screen and it comes back on the left. So we're seeing a wave flip over. Again, coming on the right, then back on the left. Now you see the wave coming back on the right, down on the right, and back on the right. This is free end, or they call it loose end in the video. Again, down on the right, back on the right. You can see here on the left, back on the left. There also is a large amplitude there at the wall. That's interesting. We'll get into that. So fixed end reflection. Let's explain that one first. Fixed end reflection is where you have a closed loop. So the end of the rope is not going to be able to move. That's denoted in the picture here by the filled in dot at the wall. If you see a picture like this on a quiz test or worksheet from me, look right there at the dot. That's the first thing you do to know whether you're dealing with fixed end or free end. Incident, remember, is the wave that's coming in. So we've sent in a crest. And if we have fixed end reflection, we will get a trough coming back. The reflected wave is a trough. So what we see is what we call an inversion here. The wave flips over. Why is it doing that? Well, if you kind of consider this wave is hitting a very high impedance material at the wall, and so what's going to happen is it's going to start lifting up at the wall, and that lifting up within the waves material is going to create a downward force for coming back into it from the wall. That's Newton's third law at work, the equal and opposite force thing. And so it's going to make the wave flip over. It's actually somewhat like when you have a little car hitting a big heavy truck. That big heavy truck makes a little car change the direction of their movement, going backwards. We see that in wave. We see that as the flipping in the inversion. This wave is in the same material, which means it's going to have the same impedance. If it has the same impedance, then you should be able to draw a conclusion about the speed and the wavelength. Yes, they are the same. Energy is conserved here at the wall, so that tells us that we are going to have the same amplitude coming in and out. We are not going to have this wave transmit any of its energy into the wall, and the frequency will remain constant. I will go into more detail about that in a future video. All right, let's talk about free end reflection now. For free end reflection, in terms of diagrams, you're going to be looking for an open loop, and that's showing you that this has an end that is free to move. So what we saw in the video we just watched is that the wave basically came back almost the same way that it came in. And so what's going on? Why is that happening? First of all, when the wave doesn't flip over, when it stays a crest like it is doing here, we call that upright. So if you send a crest, you get a crest. If you send a trough, you get a trough back. Why? Well, basically what's happening is when the wave is coming to the wall, it's just starting to lift up on the rope. And since there's nothing there to tie it down, stop it, it's just going to keep going up. In fact, if you look in the video that we just watched, it actually ends up with a very high amplitude crest at the wall because it just lifts up because there's nothing there to stop it. So the wave is going to stay upright. Of course, this wave has the same material. or staying in the same material, excuse me. And so it is going to have the same impedance the whole way through, which means it's going to have the same speed and the same wavelength. Energy is going to be conserved again here, so the amplitude of the wave is going to stay unchanged. And because it doesn't have anything to impart energy to, it's reaching the end of the rope, essentially. And then your frequency is going to remain constant. Now, what about if we do a thin to a thick rope? Now, what's going to happen here is that the wave is going to transmit some energy into that thicker rope, but we are not going to talk about that in this video. We're just going to talk about what's staying in that thin rope. And if you think about it here, this is kind of like fixed and reflection, where you're going from low impedance to high impedance. And in fixed and reflection, we saw the wave flip over. That's exactly what you would see here. The wave will flip over. It's exerting that downward force, making it flip. Now, in terms of impedance, this is the same material, so it's going to have the same impedance, which is going to give you the same speed and the same wavelength for this reflected wave. Big difference is the amplitude. The amplitude will always go down when you're doing this type of reflection, because in this case, we are going to transfer some of its energy into the new material. That is not shown in the picture here. We'll talk about that in a future video. So you just need to realize that the wave that comes back, the reflected wave, is just going to have a smaller amplitude because it's getting rid of some of its energy, putting it into the new material. Frequency will remain constant. I'll talk about that in a future video. All right, what about if we go from a thick material to a thin material? If we do this, this is a lot like free end reflection. So now we are talking about the wave is going to stay upright. Again, there's no reason for it to flip. We're going from a high impedance to a low impedance. That lower impedance material is just not able to make the wave flip over. Since we're in the same material, we're going to have the same impedance, so we're going to have the same speed and the same wavelength. We will see a decrease in amplitude for exactly the same reason that we just mentioned on the previous slide. And the frequency is going to remain constant. Again, I will point out this question mark is here on the slide to tell you or remind you that there will be a wave in the new material, in the thin material here. We are just not going to cover that in this video. That will be a future video. So in summary, whenever a wave hits a higher impedance material, it's going to invert it, it's going to flip it over. The crest is going to become a trough at that point because there's going to be a force exerted at that boundary. But if you hit a lower impedance material, the wave is going to stay upright. Lower impedance materials cannot exert forces in that way, so the wave will never flip. Since we're staying in the same material, all reflections will have the same speed and the same wavelength. You will see a decrease in amplitude if the wave is able to transfer energy to the new material, and frequency will always remain constant. That's it for reflection. If you have any questions, please let me know.